This video is on pressure in a fluid and covers chapter 15-3 in the textbook. All right, so what do we mean by pressure? So we've talked about pressure before, and if you remember, pressure is defined as a force divided by an area. So the SI units, well, force we measure in newtons, area we're going to measure in square meters. So the SI unit for pressure is the newton divided by square meter, or that's also called a Pascal, abbreviated capital P, lowercase a. However, when it comes to pressure, there's lots of other units that are commonly used. So for example, there's a unit called an atmosphere, which happens to be approximately equal to atmospheric pressure, which is about 101,000 pascals. So there's also something called a millimeter of mercury, and 1 Pascal is 7.5 times 10 to the minus 3 millimeters of mercury, and this is also related to a unit called a torr. So this 1 Pascal is also 7.501 millitorr. And there's also pounds per square inch, or PSI. So 1 Pascal is about 1.45 times 10 to the minus 4 pounds per square inch. And depending on what you're doing, you'll see all these units for pressure. So it pays to remember how to convert between them. Now, the important thing to remember, of course, is that if you have a fluid, fluids exert pressure in any, or perhaps you should say every, direction. So if you have a static fluid, so by static fluid we just mean a fluid that's not moving at all, so it's not flowing. So if you've ever been swimming, this probably isn't a surprise that if you dive down deep to the bottom of the pool, there will actually be an increase in pressure. So pressure increases with depth if you have a static fluid. Now the reason for that is actually pretty simple. So you imagine you have some little bit of your fluid here. Well, that little bit of fluid has a weight. And the weight of that fluid, well, it's going to be related to the density times acceleration due to gravity, little g, times the amount of fluid you have. So assuming that, well, if your density is varying with depth, then you have to do an integral. If the density is constant, things get a little bit simpler. But in general, this is how you calculate how much the pressure increases with depth. So if you have a constant density, well, then rho gets pulled out of the integral, and it's, well, and g, so it's just an integral dy. So if you have a constant density, then the pressure at some depth p is equal to the pressure at the top of your fluid, so that's this P0, which is typically atmospheric pressure, plus the density of the fluid times little g times h, or sometimes you see this written as y, so that's just how far deep you are in the fluid. Now, what will also happen, so if you immerse an object in a fluid, so imagine, well, a ball or a submarine, so you immerse it in a fluid, so there's going to be a pressure, and the pressure gets exerted in all directions. So the effect of that is that you expect an object immersed in a fluid, the volume of that object is going to decrease. And the amount it decreases, well, you can have this relationship that the pressure exerted by the fluid is going to be this constant B times delta V over V. So, and hopefully this should the form of this equation will look fairly similar. So B is a constant, it's called the bulk modulus, and it's a property of the material. So there's a table in your book, table 15.2, that actually lists the bulk moduli for a variety of different objects. So this tells you basically how compressible these different materials are. So now P is the volume stress, force per area, and delta V over V is the volume strain. So hopefully this should actually look fairly similar to when we did Young's modulus and the shear modulus. So the form of this is exactly the same. So you have a stress is equal to some constant times a strain. All right, so now just one other bit of terminology that in particular as engineers you'll run into this. So atmospheric pressure, right? So Earth is surrounded by an atmosphere, so we have all this air. So you could calculate, so what's the pressure versus depth in the air? And atmospheric pressure is really just the pressure due to the weight of all this air pushing on us. So in atmospheric pressure, if you're on Earth, you can't get away from it. So at sea level, the pressure exerted by the atmosphere is about 101,000 pascals, and that's where this unit called the atmosphere comes from. Now, you can also define something called a bar, and a bar is defined as 100,000 pascals. Now, when it comes to measuring pressures, and your textbook talks about measuring pressures and how you do this with manometers or barometers, but depending on how you're measuring the pressure, sometimes you refer to something called a gauge pressure. So in a gauge pressure, so that's this PG, that's the difference with atmospheric pressure. So depending on how you're measuring things and what you're measuring, this is often useful, where you don't measure the absolute or the total pressure, you're just measuring how different is the pressure from atmospheric pressure, so above or below. So, and that's the gauge pressure.